Here we're asked to find all the turning points of the curve y equals negative 3x to the fifth plus 5x cubed, and we've got to find the nature of these turning points, where they are local maximums or local minimums. So what do we think when we get a question like this? Well, turning points happen when, you ask yourself, well, what happens with a turning point? Turning point is when dy dx is equal to 0, and we've worked through a template that will actually allow us to determine the turning points. So, and then it's simply a matter of identifying the nature of these turning points. So we'll work through the template to actually find these turning points and their nature. So the first step is in the template is to find dy dx. And so we get dy dx is equal to, now when we find the derivative of negative 3x to the fifth, we multiply the power times the coefficient, we get negative 15, then we take 1 off the power to the fourth, plus 15x squared. So that's dy dx. And turning points occur when dy dx equals 0, so we've got to solve and find what values of x make dy dx equal 0. So we've got 0 equals negative 15x to the fourth plus 15x squared. And we say, well, how do we solve that? The quadratic formula won't work because it's a polynomial to the power of 4. So quadratic formula won't work. We've got factorisation that will work. As I've said in previous talks here, you can't divide by the unknown. As soon as you divide by the unknown, you'll lose one of the roots or one of the zeros. So it would be wrong, even though you've got 15x squared that's common to both there, it would be wrong to divide every term by 15x squared. I know that will make it simpler to evaluate, but you're going to lose one. So what we do is factorise. So we've got 0 equals, as I said, 15x squared is common to both those two terms on the right. Take it outside and you say, what am I going to multiply 15x squared by to get negative 15x to the fourth? So that'll be negative x squared. And what am I going to multiply 15x squared by to get 15x squared? Well, the sign comes down there and be plus 1. And probably it will be better to write that as 15x squared outside of 1 minus x squared. And you say, well, that's factorise it, but in fact it hasn't factorised it completely. We look at this second one and it is factorisable. You should twig that this bracket is in the form of a squared minus b squared, which is dots, difference of two squares. There's a square there and a square there. You can find the square root of that easily, the square root of that easily. So this is a pattern you should know, the difference of two squares, and it says that a squared minus b squared is a minus b, a plus b. So that is the pattern. So this is like 1 squared minus x squared. So this will be 15x squared outside of 1 minus x, 1 plus x. Now there is what's called a null factor theorem that says that if you've got 3 factors or 4 or 2 that multiply together to give you 0, at least one of these has to be equal to 0. So we can say, we can solve these. There's 1 factor there, 1 factor there, 1 factor there. We can solve each of those. So 15x squared equals 0, and there's only one possibility there, and that's x equals 0. Or 1 minus x equals 0, take the x to the other side and you get x equals 1. Or 1 plus x equals 0, take the 1 to the other side and you get plus x equals negative 1. By taking that 1 over the other side. So they will be my 3 turning points. So turning points are when dy dx is equal to 0 and are at x equals 0, x equals 1 or negative 1. Okay, so they're the turning points. What's the third step? The third step is to find y values, find corresponding y values, for each of these x values. How do you do that? By substituting these x values back in the original equation. So when x equals 0, y is equal to minus 3 times 0 to the 5th plus 5, 0 to the 3, which is just equal to 0. When x equals, we'll do the second one, 1, y equals negative 3, 1 to the power of 5 plus 5 times 1 to the power of 3. So that'll be negative 3 plus 5, which will be equal to 2. And when x equals negative 1, y equals negative 3 times negative 1. And it's probably good on your, either in your head on your calculator to think of that as being in a bracket. Plus 5 negative 1 cubed. So whenever you have an odd power of a negative, the answer will be negative. So this will be negative 1. Negative 1 times negative 3 will be positive 3. And then this will be negative 5. So it'll be plus 3 minus 5, which will be negative 2. Alright, so we've got our y values. So turning points, we've up ahead here, up above rather, we've actually worked out what the x values are, but now we've got the turning points at, the y values of the turning points at 0, 0, 1, 2, and negative 1, negative 2. So they are my 3 turning points. Okay, what's the fourth step of the template? And the fourth step is to determine the nature of the turning points. And that's simply a matter of applying either the first, so there are 2 ways to do this. There's the first derivative test, and using the first derivative test, you actually just put in values on either side of each of the x values. So let's look at the smallest x value first, which is negative 1. So you could actually substitute in negative 1.5 and negative 0.5 and see what happens to the first derivative, dy dx, and then that will determine whether you go from a positive gradient 0 to a negative, or from a negative 0 to a positive gradient. So that's the first derivative test, and we've just learned how to do the second derivative test. And the second derivative is to go to the second derivative and see whether what's happening with the concavity, and that will tell us whether we've got a maximum or minimum. How do you know which one to use? Probably the quickest way to do these, if it's possible, is to use the second derivative test. And the second derivative test I would encourage you to use when it's easy to find the second derivative. Now up here we've got the first derivative as negative 15x to the fourth, so way up here we've got the first derivative dy dx, forget about the 0, dy dx is equal to negative 15x to the fourth plus 15x squared. Now that's easy to find the second derivative of. If the first derivative involved a fraction and you had a function of x over another function of x, it could be quite difficult and a lot of work to find the second derivative. You could still do it, but that may mean that you just go and use the first derivative test and put those values in on either side. So I think in this case it's probably easier, we'll use the second derivative test. So we'll actually just find the second derivative and work through there. So d2y dx2, so going back up again, we are going to find the derivative of that, and we get negative 60x cubed plus 30x. So that is the second derivative. So all we've got to do is to go and substitute the x values in and see the nature, whether it's positive or negative, to determine whether we have maximums or minimums. So at x equals 0, d2 y dx2 is equal to negative 60, so that'll be 0, 0, so that'll be just equal to 0. So second derivative test fails. And if it fails, we then have to go back and use the first derivative test. So we'll come back and actually use the first derivative on that. So when x equals 1 is when the second turning point occurred. d2y dx2 equals, and if we put 1 in there, we'll get negative 60 plus 30, which is equal to negative 30. Now, because this is a negative, therefore we have a maximum. From work previously done, if the second derivative is negative, we have a maximum, a local maximum. So x equals negative 1 is where the third turning point is. d2y dx2 will be equal to, now once again when we cube, because that's an odd power, that is going to be negative, so the negative times the negative will be positive 60 minus 30, and that's equal to positive 30. Now because the second derivative is a positive value, therefore we have a local minimum. Alright, so what have we got to do still? We've got to actually go back and see what happens here when x is equal to 0. And to do that, now we've got to be very careful we don't go, when we're putting in values either side of x equals 0, we've got to be very careful that we don't go to the other side of that point. So we need immediately either side of this point before we get to x equals 1 and before we get to x equals negative 1. So we'll use probably 0.5 and negative 0.5. So at x equals 0, so we've got to go back and use the first derivative test. So we've got x and dy dx. So we'll go negative 0.5, 0, positive 0.5. And when we substitute those values in, we know when x is equal to 0 that dy dx is equal to 0. And when we put x is equal to negative 0.5, we know that it is a positive value. You put negative 0.5 into dy dx, you'll find that you'll get a positive answer, and then you get a negative, sorry, you get another positive one when you put in there. So what happens is dy dx is going from a positive, so you're actually substituting negative 0.5 into dy dx. When you put 0, you know you get 0. When you put 0.5 in, you'll get another positive value. So what happens is we've got a positive gradient, a 0 gradient, and then another positive gradient. So this tells me that we actually have neither a maximum, a max or a min. In this case, you can see that we're going to have, and we're going to talk about this in the future, a point of inflection. So when the gradient doesn't change on either side of the turning point, so the gradient's positive on one side, 0, and then positive, or if it was negative 0, negative gradient, we're stepping down, then you have what's called a point of inflection. So we can now put all that together. So at the 3 points were 0, 0, we have a point of inflection, POI, point of inflection at 1, 2, we have a 1, 2. So when we put 1 in, we get a local maximum. And at -1, and what was the one for -1? -1, -2. So when we put in -1, we saw that we had a local minimum. Okie dokes. That has addressed the question. It was not necessary to sketch it, but what would it look like with a sketch? Well, the original function was -3 x to the 5th plus 5x cubed, and so it is going to go through the origin. We have at -1, we have a minimum, a local minimum, and here we have a local maximum at 1. So, and here we have a point of inflection, so it's going to drop down, it's then going to go and then go up and over and down again. Alright, so quick little sketch. So we've got gradient going from positive gradient 0 to positive, as we found out in that table there. Here we've got a local minimum at -1, -2. We've got our local minimum, and here a bit of a scrappy. We have 1, 2. We've got a maximum. All right, you weren't asked to do the sketch, but that's just to give you an idea what it looks like. So going back through it again, when you're asked to find turning points, and this is an important part of this course, to be able to do this, is to find all turning points in their nature. Use the template, divide x, make it equal to 0, never divide by the unknown, but factorise. And then once you've got those x values, substitute in to find out the corresponding y values. And the fourth step is by either using the first derivative test, second derivative test. Second derivative test is probably the quickest to use, but if it's very difficult to have to find the derivative again, just use the first derivative test. And if you get the second derivative equals 0 when x equals whatever value, then you've got to go back and use the first derivative test, which is what we did here.